We are continuing our discussion of the quantum mechanical harmonic oscillator, and we reduced the Schrodinger equation to now a function of h, which now gives us the second order differential equation. And we're going to solve it by the method of Frobenius or a series solution. So we're going to say that h is just a polynomial where these a sub n are coefficients. They're just numbers. All right. So let's put this into our equation. So the first derivative is going to give us now, so if we take the first derivative, we essentially bring down a n. So the sum a n, or we bring down the n y to the n minus 1. Okay. And then the second derivative is to take the next derivative here, and we, this now starts at 1, right? Because we eliminated the a equals 0 coefficient. And now this becomes, starting at n equal 2, a to the n, n minus 1, y, n to the minus 2. Okay, so how do I know that? Well, if I wrote out my polynomial as a0 plus a1 y plus a2 y squared plus dot dot dot, then what I should get is the first derivative will give me a0 as a constant, it disappears. I get a1 plus 2 a2y plus 3 a3y squared plus dot dot dot. And the second derivative gives me 2 a, no, sorry. Yeah, so the a1 disappears, and you get 2 a2 plus 3 times 2 a3 times y plus dot dot dot. And that's what those sums tell me, is that when I take the derivative, I have essentially n equals 1. I start with the n equals 1 for the first derivative. Okay, so if we put these together, what do we get? We get, for the second derivative, n equals 2 to infinity, a n, n minus 1, y to the n minus 2 power. Okay, that's the first term. Second term is minus 2y, the sum n equals 1 to infinity, a to the n, n, y, n minus 1. And then we have a plus 2 epsilon minus 1, the sum n equals 0, a to the n, y to the n. Okay, so that's what, so I've gotten rid of the derivatives. It's now just polynomials added to polynomials. Now it would be convenient if we could have all of them under the same sum. And so I can do that. I can put them all under the same sum, because if you notice that if, like this first term, if n equals 0, then the answer is 0. If n equals 1, n minus 1 gives me a 0. So I can just arbitrarily, not arbitrarily, but I could shift the index such that I get n equals 0. So therefore I have n equals 0 to infinity of a to the n times n times n minus 1, y to the n minus 2, and now I get minus 2 a to the n y times y n minus 1 gives me just y to the n, and then the last term is plus 2 epsilon minus 1 a to the n y to the n. Okay. So now everything's under the same summation right there. Let me combine terms. And so if I combine the second and third term, I get the sum a to the n minus 1, y to the n minus 2. And then I get 2 epsilon minus 1 yeah, 2 epsilon minus 1 minus 2n a to the n y to the n. Okay. So now what I want to do is I want to make a shift. So now basically I want to shift this so that I can get rid of the y, or I can factor out the y, I should say. So if I want to shift this, I could take this term here, so basically n minus 1, y n minus 2, and I could turn that into n plus 2 times n plus 1 times y to the n. Okay, so because you notice you get the same thing. So if n equals 2, then I would get y is equal to y to the 0 power, and that gives me 1. And so I essentially shift that. And the one thing I didn't shift was the a to the n. And so what I need to shift is also add in a to the n, and then multiply this by a to the n plus 2. So eventually, I've actually shifted all of my indices by 2. Okay, so now let's put that together. 0 is equal to the sum of a to the n plus 2, n plus 2, n plus 1, y to the n, plus 2 epsilon minus 1 minus 2n, a to the n, y to the n. So now I can factor out the y to the n. And by doing that, I now can look at this and say the only way that this is going to be 0 if the thing in the square brackets is equal to 0. So I can rewrite this now as 0 is equal to a n plus 2, n plus 2, n plus 1, plus a to the n, 2 epsilon minus 1 minus 2n. And so now if I equate these, I now have a solution for a n plus 2, that term, is equal to 2n plus 1 minus 2 epsilon over n plus 1, n plus 2 times a to the n. Okay, And this right here is called a recursion relation. So that is my recursion relationship. What does that mean? Well, it means now if I know the first term, right, if I know A0, then I can find A2. So essentially, if n equals 0, I have to have a given A0. I just have to start with that value. That's my starting value. And that means A0 plus 2 is just A to the 2, which is equal to n is 2. So that's 2, 0, plus 1 minus 2e over 1 times 2 times A0. So A2 is going to be equal to 1 minus 2 epsilon over 2. That value right there. If I now want to get if I want to get n equals 4, I essentially have A4 is equal to 2n plus 1 minus 2 epsilon over n plus 1, n plus 2, and a to the 2. So I could plug in the value of, no, not n4. If n equals 2, then that will give me A4, which is 2 times 2 is 4, 5 minus 2 epsilon over 3 plus 4 is 12. So I can bootstrap my way up. If I know A0, I can get A2. If I know A2, I can get A4. If I know A4, I get A6. The same thing is true now with the odds. If n equals 1, I have to declare what A1 is. But now, A3 is going to be, if I add, so 1 plus 2 is 3, so now n is 1. So we get 2 plus 1 minus 2 epsilon over 2 plus 3 is 6, A1. And now I can work my way up to get that coefficient. So that's we're going to do that in a little while. But essentially what I wanted to say is if I look at this, right, that there's an upper limit. Because at some point, the numerator is going to be 0. Why is it going to be 0? Because that's going to truncate my polynomial. If I don't have the numerator equal 0, what I find is that when I plug back in these a's, then h this right here diverges. Okay, so I have to stop that polynomial from diverging, and in order to truncate the divergence, I can essentially find a place where the numerator is equal to 0, and then it stops. So to stop the divergence, I have to have 2n plus 1 minus 2 epsilon is equal to 0. Or if I rearrange this, I have 2 epsilon is equal to 2n plus 1, where epsilon is equal to n plus 1/2. So that's interesting because my dimensionless energy is now n plus 1/2. So my energy over h bar omega is n plus 1/2. So I now have the quantized energy levels. So from the recursion relationship, I've now found that the energy of every level in the harmonic oscillator is just the index n plus 1/2 times h bar omega. So we'll investigate that more in the next lecture.